Hello, my name is Brittany Jones, and I am a scientist at the National Marine Mammal Foundation. And I work on a project that we lovingly refer to as Sound and Health. Our overall goal is to develop tools and methods for non-invasively recording the vocal behavior of the Navy's bottlenose dolphins for monitoring their health and welfare. Let's call this the umbrella focus, and then we can dive into all of the different approaches that we are currently implementing. For each approach, I will introduce the concept from the human or terrestrial animal standpoint, and then follow that with a description of how we are applying it to the dolphins. Here is a dad who is cooking dinner for his children who are playing upstairs. Although he cannot watch them every moment, he can perceive a lot about their welfare by the sounds that they make. For example, if he hears this, this would likely be perceived as a positive welfare indicator, and he might not have anything to be concerned about. Whereas if he hears this, he'll probably perceive things differently. He may choose to go check on the kids or do something to mitigate the situation. We use this same idea with our animals. A great example is the furbo. I'm not going to lie, I tried to introduce this to my dogs and it scared them to death, but many people love it. The furbo watches and listens for your dog and sends you a push notification if your dog were to be barking a lot. And depending on your specific dog's typical demeanor and behavior, you might infer different things when you get that notification that they're barking. For example, maybe it is just another Amazon delivery at the door. Or maybe someone has come into your home. Maybe you use your furbo to see how long it takes for your dog to settle down after you leave the house, which you can use as a positive indicator that your dog is calm and not stressed. Programs to monitor the acoustic behavior of farm animals are currently being developed in order to improve their health and welfare as well. For example, monitoring for sounds of coughing allows for early intervention and reduced spread of respiratory infection in pigs. Over the last 4 years, we have essentially created a furbo for our dolphins. While it doesn't throw treats to them, it does monitor their vocal behavior around the clock. While the Navy dolphins get to go out swimming in open water every day, they come back and reside in open water netted enclosures in San Diego Bay. We have been recording our dolphins' vocal behavior around the clock for 2.5 years now. This is our underwater hydrophone array. Now, a hydrophone is just an underwater microphone. Our array is made up of 4 hydrophones, and this sits at the bottom of the bay and constantly records all of the sounds coming in from our dolphins and around our dolphins. Thanks to the help of Michael Oswald at St. Andrews University, we have created a free-to-download software for this around-the-clock monitoring. This PAMguard plugin is called NMMF Welfare Acoustic Monitoring System, or WAMS. In addition to the program, we have spent the last 3.5 years creating a vocal catalog for 15 of our dolphins. Each dolphin has a signature whistle, which is an individually distinctive whistle contour, which has a stereotyped pattern of frequency changes over time. We'll be using spectrograms to view whistles a lot throughout this talk. These are spectrograms. These are visual depictions of that change in frequency or pitch change over time. Time in seconds is on the x-axis, frequency in kilohertz is on the y-axis, and in this case, the lighter colors depict the louder sound. Therefore, a dolphin's signature whistle always appears to have the same relative shape when viewed on a spectrogram. Here are a couple examples. You can see how they're individually unique. Signature whistles are produced most commonly when the animal is separated from their group because the signature whistle broadcasts the animal's identity. Now that we know what a signature whistle is, let's see how we can utilize this information with our around-the-clock recordings. Using WAMs, we have developed a baseline typical vocal behavior graph for our group of dolphins. The center line shows you the mean whistle behavior during each hour plotted on the x-axis for our group of dolphins. You can see the extended shadow in light blue depicts 2 standard errors above the mean. You can see that during our nighttime hours, the vocal activity is very low. This is perceived as a positive welfare indicator that our dolphins are getting adequate rest. You can see that the vocal behavior picks up about the time our animal care staff arrives in the morning and the animals remain chatty throughout the day. When the vocal activity follows this typical pattern, we assume all is going well. If there were to be a large increase in whistle rate, if there were to be a big spike in whistle activity outside of the normal range, our team would get an email notification with an image of the spectrogram so that we can see what's going on. We know, thanks to the localization abilities of our 4-hydrophone array, whether that whistle rate spike was coming from the female dolphin side or the male dolphin side. And because we have that extensive vocal catalog for each animal, we can make an educated guess about what dolphin may be the one responsible for that spike in whistles. If this behavior were to persist, we could reach out to the animal care team and have them go take a look at that dolphin and make sure everything is okay. Let's go check in on that dad who is cooking dinner, because he just heard a loud crash. Although he knows that sound did not come from his kids' mouths, he knows that it came from the area surrounding his kids. He will likely react by going to check what happened and make sure that everyone was okay. We similarly monitor the dolphin's environment for loud sounds that are in the dolphin's hearing range. Did you know that most boat sonar is actually out of the range of human hearing? This is done intentionally so that we don't cause hearing loss in our operators, and it is harder to detect by listeners. Unfortunately, the dolphins have excellent hearing in this range. They can even hear over 160 kilohertz. So oftentimes these sounds are right in the sweet spot of dolphin hearing. They can also mask dolphin vocalizations by putting a loud sound right in the frequency range that dolphins need to be able to communicate. All of that around-the-clock acoustic data that we're collecting with that array and analyzing with WAMs then gets passed to a second program called WaveWatch that was created by Dr. Jason Mulso in LabVIEW. This scans those recordings for sounds that are abnormally loud and weights them by the dolphin hearing curve. So it's not so concerned if the sound is loud, but outside of the dolphin's hearing range. This also can trigger alarms to the research team if a sound is recorded that is over the user-defined threshold. This allows us to identify those loud sounds, pass that information up the chain of command for mitigation efforts if that sound is perceived to be too loud. All right, now that we are monitoring the dolphins' vocalizations and the sounds in their environment around the clock, now it's time to zoom in. Let's look at their vocalizations a little more closely. We have all experienced a loved one when they come down with a bad cold. And some of the first things that we might notice when they start getting sick are the changes in their voice. For example, those raspy or nasal characteristics might let us know that they have a respiratory infection. But what about other things? What if we hear a slowed, quieter speech rate? Might this also suggest that something is wrong? Absolutely. We often can tell that someone is down, depressed, or exhausted based on these types of changes in voice. How might you perceive the internal state of a human who is talking fast and with scattered thoughts and loud? There is actually a massive push right now to develop telehealth applications for identifying different disease states from voice. And the last 5 to 10 years has really been remarkable in the strides they have made. Some of the early research coming out of this field are using voice to predict things like Parkinson's disease, Alzheimer's, COVID-19, depression, heart disease, all from voice recordings that people can do from the comfort of their own home. Here's a little clip from a company called Sond that I think does a really good job describing this idea.
At Sond, our mission is to unlock voice as a vital sign and predictor of health. We're harnessing this information to bring voice-enabled health detection and tracking to the world. For example, when speaking with someone you know well, within seconds you can notice they don't sound like themselves. Maybe the person is sick, tired, or feeling down. You're intuitively listening to vocal biomarkers. Our voices contain vocal biomarkers that give valuable information about certain health conditions every time we speak. With Sond's proprietary machine learning technology, derived from millions of data points coming from tens of thousands of Sond users, we have built intelligent tools that track health changes by analyzing just a few seconds of voice.
So in order to even begin to assess whether we could successfully use this same approach with dolphins, the first thing we needed to do was to find out, what do our dolphins sound like when they're healthy? The first thing we set out to do was to create those vocal repertoires for each of our dolphins. This included, what types of whistles do they make? What types of whistles do they share with one another? What are the features and characteristics of their signature whistles when they are healthy? Although we first set out just to look at signature whistles, we quickly noticed with our group of dolphins that many of them were producing a shared whistle contour. We termed this whistle the group whistle. Here are some examples. You can see the signature whistle for each of the dolphins on the left side of the screen, which are obviously distinctive from one another. But on the right is each of those different dolphins producing the group whistle. And you can see how similar the group whistles are to one another, even when made by different dolphins. In order to make sure that this pattern we thought we were seeing was true, we brought in naive observers, and we asked them to do pairwise comparisons to grade the similarity of all of these pairs of whistle contours. We also used discriminant function analyses to statistically test this. It was unsurprising that each animal's signature whistle was highly similar to all of that animal's other signature whistle emissions, whereas two different dolphins' signature whistles were quite different from each other. A dolphin's group whistle was still most similar to other renditions of that same animal's group whistle. But you can see here that one dolphin's group whistle was also extremely similar to other dolphins' group whistle emissions. A discriminant function analysis also confirmed this. In this graph, each color represents a dolphin, and each signature whistle is depicted as an open circle. As you can see, all of the signature whistles cluster with all of the other signature whistles from that dolphin. The group whistles are depicted by solid circles. And the group whistles all cluster tightly together, regardless of which dolphin produced it. And they do not cluster with their own dolphin's signature whistle. If we head back to that bar graph, what was interesting was that a dolphin's group whistle was more similar to other group whistles from that same dolphin than it was to group whistles produced by other dolphins. This may be useful for other dolphins to be able to perceive which dolphin is producing the group whistle. If you're interested in learning more, please read our manuscript in +1. Now that we have developed a robust vocal catalog for our focal dolphins, we started working with Dr. Abby McLean, a veterinarian, to develop our health definitions. These definitions define what it is to have normal and abnormal health for our focal animals. Lucky for us, our population of dolphins are extremely healthy and receive top-of-the-line medical care. That said, it takes some time to build up a data set of abnormal health days in our focal population. While we continue building these data sets, we have worked with Risa Daniels and the Veterinary Records Office at the U.S. Navy. They are able to translate our health definitions into scripts that are able to query the U.S. Navy's extensive health database for each dolphin. These queries give us an output for each date that we have a recording for that animal on whether they fit into our optimal health category or abnormal health category on that date. These dates are confirmed by health data and veterinary observations. We are so grateful to the Office of Naval Research, who has just funded the second leg of this project. We are collaborating with Jeremy Karnowski, a data scientist, who is helping us build machine learning and deep learning models for taking all of that data that we have been collecting over the last 3.5 years and training models to be able to output or predict health status from whistles. Like we touched on earlier, one of the fastest growing industries in human healthcare is developing artificial intelligence technologies to be able to identify and early predict health status changes from vocal biomarkers. The technology that is at the forefront of this innovation comes from deep learning neural networks. These begin with inputs. So in our example, they would be speech segments, which then are passed through several layers of connected neurons that progressively detect features and characteristics from the inputs without human interference, and are trained to be able to provide an output, which is typically a classification. These models remove human biases, and they can find relationships and interactions that may not be obvious to human analysts. Deep neural networks have shown great success in being able to identify marine mammal sounds from other ocean sounds, such as background noise, ships, and other anthropogenic noise sources. And they have also shown great success in classifying different marine mammal species vocalizations from one another. A recent study was even able to train a small neural network to successfully identify chickens with bronchitis from healthy chickens, based solely on their vocalizations. In order to try and do this for the first time with dolphins, we needed to decide what our input should be. The most efficient computing option is for the model to use the raw audio data, or 1D file. But because there has been so much development with computer vision, there is actually more of a foundation to be built upon if we were to use the spectrogram images as our input. And to be best able to talk about what variables actually change with changes in health status, we needed to run some models using the hand-coded variables, such as maximum, minimum, start, end, frequency, duration, etc. But that input is extremely time-intensive. We also have 2 different output goals. The first one being that the model could predict which dolphin produced the sound. And then, of course, the next step being that the model could predict the health status of that whistling animal. The random chance of assigning a signature whistle to the correct producer by just naively guessing was between 9 and 16.5%. Our current model, using only the audio wave file as the input, and deep learning strategies, was able to correctly assign the whistle to the correct dolphin almost 90% of the time. As we mentioned, the main goal of the project is to be able to not only predict who made the whistle, but further whether the dolphin was in a thriving, healthy state or an abnormal health status when they made the whistle. In order to start to build this, we used all of the whistles produced by a dolphin, not just their signature whistles. And the random assignment of a health status for any given whistle would result in a success rate of between 59 and 65%, because we have more recorded healthy whistles than we do abnormal whistles. Using that 1D wave file as the input for 5,055 whistles recorded from 11 different dolphins, the gradient boosted classifier was successful at predicting health status from the whistle features, regardless of the producer, almost 86% of the time. What was really interesting is that in only 4.5% of the whistles that were misclassified was the program giving a false alarm. So classifying a normal health whistle as abnormal. This is a great false alarm rate. The rest of the mistakes came from when the classifier classified the animal as healthy based on their vocalizations, when the health records depicted that there was something abnormal going on with that animal. This is actually an exciting error to have, because this might suggest that depending on the type of health condition, might affect whether the voice changes. These are the very preliminary results with sort of the first round of models that we've done, so we are looking forward to the next steps and to continue building our data set and improving upon these models. We have recently began to develop a new data set of whistles for use in developing these applied tools. These new recordings we have called acoustic physicals. We have just begun training our vocal dolphins to sink underwater and then produce their signature whistle when asked using a hand signal. This idea comes from those being deployed by the human vocal biomarkers applications. When you are healthy, you read a few predefined sentences when prompted by the app. And then when you are feeling unwell, you read those same sentences. And that helps the app to be able to learn what voice features change during different changes in your health status. We are hoping that dolphins that are asked to produce their signature whistles will have similar modifications as found in their spontaneous whistles when they experience a change in health status. We have just begun building this new data set. This will allow us to record whistles quickly from each dolphin nearly every week, instead of on an opportunistic basis, and build up a new data set that covers a larger array of health changes. This further allows us to incorporate a larger group of dolphins into our data set, which provides more generalizability for potential uses outside of just our focal group. For example, the potential use for conservation. Phew, that was a lot of ground that we just discussed. So let's put all of these seemingly separate pieces together within a larger picture. The ultimate idea would be that our dolphins could be going about their day whistling, and our underwater array would record those whistles. Then it would pass that audio to our neural network. Our neural network would use that 1D audio file and be able to give us a prediction for which animal made that sound. A second neural network would then have access to the sound's features and information about what animal most likely made that sound. And then it would output a second prediction on whether that dolphin sounds totally normal, or if their whistle sounds more similar to those that they have produced when they weren't feeling well in the past. How cool would that be if we could passively record the dolphins and get early warning signals of changes in health status? That about wraps things up for what we have been up to and are endeavoring to accomplish here in the Sound and Health Project at the National Marine Mammal Foundation. If you're excited about these ideas, have any questions, or are inspired for a collaboration, please reach out to me at my email address, which will be on the next slide. Thank you to all of the people that are listed here, without whom the project would not be able to happen.